The ideas in today's lesson that we're going to cover will be observations and inferences. What exactly is going on with these? So, by the end of the lesson, what you should be able to do is describe what an observation is, what an inference is, and how they're important with respects to scientific skills. Now, we also need to be able to differentiate inference from a prediction. So there's some differences there. All right. Now, throughout the semester, you should keep a list, whether it be, on your computer, in a Word document, on a piece of paper, in your notebook. You should keep all of the key vocabulary that we're going to use in all the lessons, because they are going to show up all the time on the quizzes, on the tests. When it comes to the end of the semester and you have the semester exam, it's going to show up there. So it's wise just to start keeping a running list of all of the terms that we're going to use. So the terms that we're going to use today, we're going to look at observing, predicting, inferring, observer effect. We're also going to throw in a few other ones. So you can add those as we move through here. Okay, so let's start. Essential question. An essential question that we need to ask is, why is observation and inferring an important scientific skill? Well, inferring and observing things, they are very important because they help to establish ideas. They help to establish theories. For example, the theory of natural selection. If we're looking at the theory of natural selection, it comes from the basis of making observations. Now, what I'm going to show you is a small little video clip on the natural evolution of the peppered moth. How has that peppered moth changed throughout history? What has caused those changes? What did we observe to see as the changing, or the factor that's going to be causing the change within the peppered moth population? So we'll do that right now.
The peppered moth is a species of moth found in England. There are two variations of color in the species. Some moths are white with dark speckles, and some moths are dark with light speckles. The peppered moths live in environments with light-colored trees, like birch trees. Which moth do you think has an advantage in this environment? Can you find the moths? There's one more, do you see it? The light-colored moths had an advantage for survival. Their color helped them to blend into their environment and hide from hungry predators like birds. The dark-colored trait was a disadvantage. Moths with this trait were more easily spotted by predators and had a lower chance of survival. Since the light-colored trait had an advantage for survival, it was more commonly seen in the population. This was due to natural selection. Individuals who are best suited for an environment survive longer, reproduce more times, and pass on their genes. Natural selection over many generations can cause noticeable evolutionary changes in a species, and the peppered moth is the perfect example. In the 1800s, the Industrial Revolution took place. Manual labor was taken over by machinery. Factories began to produce goods. These factories were powered by coal. The burning of coal released a lot of pollution. Dark clouds of soot and ash lingered in the air and even settled on the trees. Over time, the once light-colored trees were covered in a layer of dark soot. Which color variation had the advantage after industrialization changed the environment? The dark-colored moths now had the advantage. They were able to blend well into the soiled trees, while the light-colored variation stood out. Light-colored moths were more easily spotted by predators and had a lower chance of survival. They reproduced less often, and the frequency of this trait decreased over time. The dark-colored moths increased in frequency after many successful generations of survival and reproduction. But this story has one more plot twist. It didn't take long for people to realize that air pollution was a major problem. Laws were put into place, and factories began to reduce their emissions. The skies were once again clear, and the trees as well returned to their natural light color. As a result, over time, the dark moths decreased in frequency, and the light moths became the more common variation once again. This is evolution by natural selection.
So from our video, what they were able to do is they were able to observe that peppered moth. They saw the peppered moth on the birch tree, and they could see that the black peppered moth stuck out more when environmental conditions were clean. And as the pollution increased, the population of the white and black speckled peppered moth started to decrease, and then the black peppered moth started to increase. So that observation was done by sight. So what are some other senses that we can use to observe other than sight? Well, if you're going to hear something, taste something, smell something, feel something, all of those are senses that help to tell us about the natural objects and phenomenon that exist in the world around us. All right. So you as an observer, you gather information from whatever you might visibly see, smell, touch, feel. All right. But the important thing is that as you are being an observer, you're not intervening with things. So as an observer, that strictly is to observe. It's not to interfere with things. So as you are observing and you're gathering all this information, what we do with that is we start to process it and start to make some inferences. We want to communicate what we're finding. We want to predict what is happening or what's going to happen. We want to measure and classify things. All right. So all of those 5 senses can be used to gather information, to gather data that we can compile together to maybe form a new theory, to maybe come up with a mathematical law. So there's all kinds of things that we can do, but it all starts with an observation. All right. When you are using those 5 senses, some problems can occur. All right. For example, if you were going to taste something, which it's not the wisest thing to go, let's say, in a chemistry classroom or out in the woods, and then you just start randomly tasting things that you don't know what they are. That could have some bad consequences on you. All right. So there are some things that it's not advisable to observe. Okay. But you also have to realize that, let's say that you are going to taste something. All right. You go to a coffee house, let's say, and one person tastes a coffee drink or orders something, and somebody tastes it and says, "Ooh, that tastes real good, real yummy." And then the next person comes up and they drink that exact same drink and they say, "Ooh, that's terrible, it's bitter." See, observations, for example, like taste or smell, they can be subjective. One person might view it as a very tasty thing. Another person might say that it's bitter and disgusting. So these observations, they can be subjective and they are susceptible to errors. So some negatives can come from that. All right. One problem that we encounter throughout the scientific field is that observations may affect the process of being observed, which results in different outcome than if the process was unobserved. All right. Now that's a real wordy way of saying this. What we're looking at is when you go to observe something, just in the act of you observing it, you alter it inadvertently. Okay, now if you go to observe something and you cause that object to be changed, that's called the observer effect. All right, so there are ways that we can reduce that observer effect. Okay, so that way we can account for those differences. All right. Now, each time that we have those changes, we need to take into account that there are some errors associated with our measurements or with our observations. And that's where accuracy and precision of our instruments that are being used comes into play. So what is a good example of this observer effect? How can me observing something, how can that inadvertently affect the outcome? So let's see where this can actually take place. All right, where do we have an example of this? Well, let's say that you go to take a measurement of how much pressure of air is in your tire. You take that tire gauge, you press it down on the stem of your tire valve, and all of a sudden you get a little bit of air that leaves. Well, you, in trying to observe what the pressure inside of your tire was, you inadvertently let a little bit of that pressure out. So you caused a change in the pressure of that tire, and now it's not actually what it was before you went and tested it. So that caused some error in the measurement in our observation. And again, we go back to that idea that we can't just dismiss that. In science, we want to be as specific as what we possibly can. We want to try to share information that's as accurate and precise as what we can actually get, right? And that goes to the use of our instruments. There's all kinds of different instruments. If you're trying to measure out the mass of an object, you would want your triple beam balance to go to at least 3 or 4 places past the decimal. If you just had it to every single 1 gram, that's not a very accurate instrument. You're not going to be getting a very good quantitative measurement from that. That's a poor instrument for that. All right, so we have an idea of what a observation is. Okay, using our 5 senses. There are 4 types of observations that we can use our senses to gather information with. All right, so our first one is called natural observation. Our second one is staged observation. Now, those 2 types of observations are what we use to lead us into identifying theories. For example, that first peppered moth idea. That peppered moth idea, what we got from that was natural selection. All right, so that theory of natural selection comes from us using our natural observation. Okay, now our last 2 types, they collect data from actual experiments. So if we have something that's a quantitative observation, quantitative, you've got some quantities, some numbers. And then our last type of observation might be a qualitative observation. A qualitative observation is let's say a feeling of how warm it is in the room. How warm is it in the room? Well, one person might describe it as real warm. Somebody else might describe it as hot. Somebody might say, no, it's kind of chilly. Well, you're describing things based on feelings, and that's not a real good observation or good way to measure things, because there's too much of a chance that we're going to get some subjective analysis, some subjective observations. It's not going to be as concrete as what, let's say, a quantitative observation would be, with the temperature in the room being 74 degrees exact. Okay. So our natural observation, what exactly is that natural observation? It's going to occur when scientists watch and wait for the event to happen during an experiment. Okay, so we looked at that example of our peppered moth, but let's take a look at another example. All right, for instance, Sir Isaac Newton theorized that there was a force called gravity. All right, and after he watched an apple fall from a tree, this would be an example of natural observation. Newton saw something happen in nature, and without any intervention on his part or anyone else's, the apple fell. All right. For this type of observation, it means that that scientist is going to wait and wait and watch for that event to happen during that experiment. So we didn't interfere with the peppered moth. No one shook the tree for the apple to fall. So that is an example of natural observation. All right. Now we have our second observation. This is a staged. So a staged observation, it directs that the experiment that comes from the observation will have to be recreated. All right, let's take a look at an example with this. So we're going to use our good old buddy Isaac Newton again. And he came up with this theory of gravity after the apple was fallen from the tree or the balcony. And during his observation, we would characterize that as being staged, because if he's standing there and he is dropping the apple from the balcony, or if he's in the tree and he drops the apple, he's the one dropping it now. Okay, so he is staging the apple to fall from the tree. He's not letting it naturally fall on his own. Okay, so if he is the one that's causing it, many experiments begin this way. All right, the scientist thinks, what if? What if I drop this apple from the balcony? What's going to happen? All right, will it fall? All right, in this form of observation, the scientist creates the hypothetical theory, okay, from thinking about something in nature, intervening in nature, and then observing the event. Okay, so that type of observation generally dictates that the experiment that comes from the observation can and will have to be recreated. All right. So let's take a look at our third type of observation. Our third type of observation is that quantitative one. Now, quantitative observation happens during an experiment which employs mathematical models and relies on the scientist to collect information based on numbers. All right, here you go. This is an easy way to remember this. If you look at the prefix of this word, all right, the root of our word, quantitative, quantity. Quantity, I deal with numbers. All right, so if I'm dealing with numbers, then I can collect data. It is going to be an exact value. And from those values, I can come up with mathematical models to try to explain what it is that I'm seeing. All right. All right. Now we have the qualitative observation. This is when scientists perform an experiment that requires observation concerning the quality of what has happened in an experiment. All right. So these are a little more subjective. All right. For that example I used with the taste of the coffee, how warm or cool it is in the classroom. All right. Qualitative observations can be easily dismissed in an experiment that require hard mathematical data, but they're made nonetheless. You can't just dismiss how warm it is in the room, how cold is it in the room, just because there aren't any numbers associated with that. We don't want to just do away with it, but when you're looking at that qualitative observation, all right, there is a certain level of interpretation that has to be employed for us to actually use that information properly. Okay, so let's take a peek. What would be an example? What would be an example of two observations that we have here? All right, now the impulsive person would look at this picture and say, oh, an earthquake happened here because the road is split. Well, that's not an observation. All right. If I'm observing something, I am looking at it, I'm tasting it, I'm feeling it, I'm hearing it, and I didn't have any of an earthquake mentioned in those observations. All right. An earthquake is not an observation in this picture. That's not the right thing. Okay. So earthquake, not an observation for this picture. What can be an observation for this picture is there's a crack in the ground. All right. Power lines are down. Apples on the ground. Building is on the ground. Okay. Road is split. those are observations. We can't say that an earthquake is an observation because we did not see it happen. Okay, we did not witness it. All right, so we'll get into what that would actually be in just a moment. Okay, now let's take a look at the difference between predicting and inferring. Predicting is making a forecast of future events or conditions expected to happen. All right, so if we're looking at predicting something, a good example of this would be if you wanted to predict what future ozone levels were using historic data. All right, so if you were trying to identify or predict what future ozone levels were, you'd have to look at some relationships between ozone levels in the past, measurements of temperature, solar radiation, etc. Now, you'd use that information, you'd use that to help identify or to create models to give you a good representation of what you believe to happen later in time. Okay, so a prediction, you're trying to use some information to create a model to identify what would happen in future events. All right, now let's take a look at inferring. Inferring means that you're making an early conclusion based on certain observations. All right, now not all inferences are going to be correct. All right, some of them are going to be incorrect, and that happens, and that's called a fallacy. All right, so what would be an example of this? All right, so what exactly is an inference? We're going to use that example of the ozone level again. This time, instead of us trying to predict what future ozone levels are going to be, instead, what we're going to do is, let's say that you want to understand how ozone levels are influenced by temperature, solar radiation, wind. So we're not trying to predict what the ozone levels are going to be. Instead, we're going to try to understand how those things influence the ozone levels. All right. So based on those pieces of information, what we can do is we can again create models and then interpret the role of the features on those measurements on how they are going to influence or how they are going to be affecting the ozone level. All right, so the temperature, solar radiation, how are those things based on the models? How are those things going to affect or influence our ozone levels? So when we're making an inference, we're trying to figure out how those smaller parts are affecting the larger as a whole in this case. So we now know what observations and inferences are. Okay, let's get into some reasoning. If we're using deductive reasoning, deduction is a type of inference which drives logical conclusions from premises known or assumed to be true. All right, so an example of this. Let's say that we're looking at the scientific method. The scientific method uses deduction to test hypotheses and theories. All right, so it's a form of validating reasoning. All right, so let's look at an example of this type. All right, if we were to say, for example, all men are mortal. All right, so that's a statement. Harold's a man. We have an observation. Therefore, Harold is mortal. So when we're looking at that, for deductive reasoning to be sound, the hypothesis must be correct. And it is in this case. All right. It is assumed that the premise, all men are mortal, and Harold is a man, that's, in this case, it's true. Therefore, the conclusion is logical and true. In deductive reasoning, if something is true of a class of things in general, it is also true of all members of that class. Okay, so we wouldn't have to say Harold if we'd say all men are mortal and Tom is a man, therefore Tom is mortal, we have deductive reasoning. All right, now let's go to the second part here. We have induction. Induction is a type of inference from particular premises leading to universal conclusions. All right, it's a little different. All right, see, if you're looking at inductive reasoning, all right, inductive reasoning is the opposite of deductive reasoning. Inductive reasoning makes a broad generalization from specific observations now. All right, so let's look at an example of inductive logic. All right, I pull a penny from a bag, or I should say this way. The coin I pull from a bag is a penny. It's being very specific. I have a coin, I pull that coin from a bag, and it's a penny. Now, that coin, if it's a penny, and then I pull the second coin from the bag, and it's a penny, and then I pull a third coin from the bag, and it's a penny, I would say, therefore, all the coins in that bag are pennies. All right, so we're saying from something very specific, from a few pulls of coins that I take from that bag, I am making the inductive inference that every single coin in that bag universally has to be a penny. Now, is that always going to be true? No. Okay. So inductive reasoning, it does have its place in the scientific method. All right. Scientists do use it to help form hypotheses and theories. And we all know that hypotheses and theories, they can be changed. They're not always correct. Okay. So it does allow them to apply theories and to specific situations. There is a purpose for it. Okay. So we just looked at what inductive reasoning would be. All right. So when a conclusion is inferred from multiple observations, that's what, again, we refer to as an inductive reasoning. That may be tested throughout additional observations to see if that's true or not. All right. But if we get to abduction, it's another type of inference that is used to best explain things. All right. Now, abductive reasoning is scientific reasoning that doesn't fit in with inductive or deductive reasoning. All right. Generally, it starts with an incomplete set of observations. There's things that are missing. All right. So we're going with what the likeliest possible explanation for observation might be. All right, so let's take a look at an example of this. Let's say that you walk into your living room and you find a whole bunch of papers that are torn up and they're all over the floor. You don't know what happened, but your dog is in the room. Okay? You don't know that your dog has torn up the papers. You didn't witness it, but the dog was in the room all day long. So what's the most likely scenario? The dog tore it up. But what you may not have seen is maybe your brother or sister went in there and they did it. All right. But since you aren't aware of it, you do know the dog was in there. That's the most probable theory that you can come up with. All right. So that is the most likely reasoning why the papers were torn up. That's abductive reasoning. Okay. So to wrap us up here, if we're looking at this picture, all right, I said that we were going to come back and we were going to justify what's going on with our picture here. We know the observation that the apples are on the ground, the building is on the ground, the power lines are split, etc. Those are all observations, but what's an inference? All right, so an inference, we're taking these observations, and based on those observations, we're trying to come up with an assumption based on our prior knowledge as to what caused that. All right, so we know that earthquakes cause fault lines in the ground. Earthquakes shake the ground. So more than likely, an earthquake has come through It's caused the building to collapse, the apples to fall. Maybe if you don't like the earthquake inference, maybe you'd say a strong wind came by and knocked down the power lines, a storm came through. But that's again an inference. You're taking those observations. You know in the past that power lines can be knocked down from strong winds. Okay. And with that, that will wrap us up for the day. If you have questions, make sure that you ask for some help. If you are completed and you're satisfied with all of your answers, make sure that you submit your work to Schoology.com. That will do us for today.